All right. So yeah, we're gonna talk about something new today, right? So it's called deep contextualized representations, and I put the transformer here in the parentheses because the transformer-based model is the most typical example for these so-called deep contextualized representations. And actually, I mean, nowadays people will not use the the term deep contextualized representation so often, but people will directly call transformer-based models, transformer-based encoders, or BERT-like models, GPT models, and so on, right? But I think it will make more sense if we follow the line of history, like to look at how these type of models are, gradually developed. Okay. I said gradually, but it's actually a very rapid, very rapid evolution. Okay, so this type of technique is basically to take care of text data, which is to understand the meanings of not just short pieces of text, but longer pieces of text, longer sentences, longer paragraphs, how to understand the semantic meanings of different entities in the text. So it's designed to solve such a more complex text understanding and the text generation tasks. Okay, but the basis of it, I would say, it's originates from the so-called embedding and the RN-based technique. So that's why I will put this chapter as the next one. That immediately follows the RN and the embedding technique. Okay, and so let's look at some first of all some milestones. Okay, so it's actually in 2018, which is some of the major achievements that have been developed. So first of all, the BERT model, which is short for bidirectional encoder representations from transformers, right? So you see the nature of the text is actually lies here within the transformers. Okay, and of course the bidirectional architecture also is important. Okay, so those are the benchmark scores that are commonly used in NLP tasks. Okay, so in that year, a lot of improvement has been achieved. Okay, and most importantly, those percentage numbers doesn't make like very straightforward. Like it doesn't make very straightforward sense to readers, but actually these are very significant improvements because some of the tasks, the models can outperform human performance, right, by a significant factor in terms of accuracy. Okay, so which means this is a very amazing achievement. Okay, so, and other than BERTs, we have some variants of it. Actually, those type of models are developed simultaneously. They came out in parallel and by different companies. The GPT model, generative pre-training model, which also uses transformers, but is developed by OpenAI. It was also released in 2018, and then GPT-2 in the next year, and now we have GPT-3, right? So those models also, this GPT model also improves the accuracies by very significant amount of tasks. So like those big companies, they have very strong competitions ongoing, right? And what's behind GPT-2 and GPT and BERT models are also actually rely on the same technique called transformers. Okay, so I think this is a example showing what kind of particular specific NLP tasks look like. So it's an example from the Stanford question answering task squad. Okay, so the data sets contains a paragraph that have some knowledge for the model to read, right? and it comes with several questions like which an NFL team represents AFC at Super Bowl 50, right? So the model should be able to generate correct answers among such options, right? So it's like a basic multiple choice question answering task, right? So basically the model should able to generate those tasks automatically based on some pre-trained model, using some pre-trained model. Okay, and the pre-training task, the pre-training technique is someone we will focus on in this lecture today and on Thursday's lecture. I don't think we will have time to cover everything today. Okay. All right, and let's look at the outline. So the first technique that we will cover today, actually, it's have a stronger connection to the word embedding techniques we just finished yet. Okay, just finished talking about. So the first type of technique is called ELMo. Okay, which is also developed in 2018, and it is in this work in the ELMo paper that's the term deep contextualized pre-training or deep contextualized representation is first developed. Okay, and the difference from these ELMo from other GPT or BERT or other more fancier network is that the model used here is significantly smaller, which is LSTM, but not transformer or transformer based models. Okay, so I think it makes sense to directly look at the first step from word embeddings to ELMo. Let's look at how that transitioning happens. Okay, so the word embedding, as we know, it's a way to represent words with dense vectors through some unsupervised learning, right? Because we just use the data alone to train itself, right? For example, we use negative sampling, right, to sample some words outside a fixed window, and in together with the positive example, we construct some loss functions, which is similar to multiple logistic regression tasks. So that will result in the word vectors that can be used, that can be plugged into some downstream supervised NLP tasks, such as sentiment classification, such as question answering, right? So we have shown that the word embedding is successful in increasing the performance for those NLP tasks. Okay, so it has very significant advantages over one-hot encoding, right? We will represent all those words with those embedding vectors, right? So these are just the example that we already know, right? So we will talk about the shortcomings of the word embeddings in traditional models. Okay, so in the word2vec, right, we will use the word orange, for example, as the context to predict the target word within the short window, right? And so each word is converted into a embedding vector, right? 300 by 1 vector, right? Right. So these conditional probability using the context word predict text word is modeled by this softmax regression probability, and then which is also approximated with negative sampling. But we know the details of the technique, right? And we know that this pre-trained network pipeline is successful in coming up in obtaining meaningful word embedding vectors. But also it comes with disadvantages of with the words embeds word embeddings trained in such a way, because first of all, each word, is represented by a single embedding vector, right? Which is a problem, right? Because we know that it's very common that the same word has multiple senses that are not even closely related, right? So I think it's more so in morphologically rich languages, okay? That is a problem that traditional word-to-vec models doesn't handle really well, okay? And in that case, because we will show that with a particular example for the word orange, because orange is a color, and orange is also a fruit. So in that case, if we don't distinguish those different, different meanings, then the vectors learned is actually a mixture of static semantic meanings. Okay? It's just a mixture of different meanings, right? So in linguistics, I think it's called the phenomenon is called ploy-semi, okay, which means the word meanings may be different depending on the context, right? So the orange juice means fruits, but paint this part oranges means color, okay? So actually, if we think of the nature of word-to-vec, actually word-to-vec knows the word orange can be color or fruits, right? But it actually does not know when to use which. No, so because the whole sentence, when this whole sentence is fed into a word-to-vec model, the model knows that the word orange co-occurs with the word paint, for example. Okay, so actually the model captures this co-occurrence relationship. It knows that the word orange means paint. Okay, and also in another language, in another word, the model knows the word orange co-occurs with the word juice, right? It also knows the orange has some meanings related to juice, but it doesn't really know which semantic meaning to choose, right? It only has one representation. Okay, it doesn't have separate representations. So here's the shortcomings of the traditional word embedding methods. Okay, so here we have a new target or new goal, which is to come up with more context-sensitive representations, right? Which is we will hope the models to be able to, dynamically adjust the word meanings by the context it reads. Okay, we hope that when the model reads the word paint, for example, it should able to adjust the embeddings for orange so that it's tuned towards a vector that represents colors, meaning, okay? And when the model have the juice within the neighbor of word orange, it should able to adjust the meaning of orange so that it's closer to the fruit type, okay? So we wish the models to be dynamic, to be flexible in doing this dynamic adjustments. So that's why we developed people first developed this first type of deep contextualized pre-training or deep contextualized model called ELMo. Okay, and it utilizes the LSTM structure. Okay, so we'll take a look at this. Interesting model. Okay, so it's called embeddings. So the ELMo is from embeddings from language models. Okay, so within each cell here, it is a LSTM cell. Okay, so the LSTM cell carries like an activation cell and a memory cell, right? and also a bunch of gates within each of those blocks. So you see, if we only look at one component, like if you only look at this left part without looking at those right parts, okay, so it looks like it's just a bidirectional. It's actually just one directional, but 2-layer LSTM, right? It's one directional, right? So one directional is here, and the above is just a second layer of one directional. So it's just a kind of a LSTM model, and the embedding for the first word, second word, the last word in a sentence. So this is a whole sentence, is fed as the input to those 2-layer LSTM network, right? And the internal activations is used as the input for the second layer, and the output from the second layer is used in the final output, right? So that is the one direction, okay? And the model also creates a second direction, which is in this way, right? So the blue color is second direction. So it's a little bit different from the bidirectional LSTM, but eventually the part on the right is from modeling the sentence from the right to the left, okay? Right, and the output from this second layer LSTM is used as outputs, and these two outputs are concatenated or sum up as the outputs for the final token. Okay, so these T1, T2, and Tn are the output representations for each input tokens. So that is the so-called ELMo model and the ELMo representation technique. Okay, so these tokens here, T1, T2 to Tn, are used in the prediction tasks. Okay, okay. So the when the model is being trained, the left to right language model, highlighted by this color, actually it's a language model. So it's maximizes the conditional probability given the current word, given the previous words for the current word, right? So it's a language task, and for the right parts, it is a right to left language model, and its task is to predict the next word by maximizing the probability of the next word given the context on the right. Okay, so this is the context that have greater than 1, right? K plus 1, K plus 2, which is all the words on the right of a model. Okay, so having these two models trained together, we are able to obtain some meaningful representations from the model's activation layers. Okay, so on the next slide, we're gonna show a simple showcase for the 1-layer LSTM model, right? And the internal is just like this, okay? And the multiple layer is just the stack of multiple activations, okay? So the training of this ELMo model is actually a joint training, which means that we are training both the forward, which is the left to right language model, and the right to left language models at the same time. So we have two probabilities, right? Two probabilities that are maximized. So these two probabilities are maximized at the same time with they are fed into the same, they are constructed, they're used to construct the one cost function, okay? So after the model is trained, so far, any questions about this architecture, model architecture? Okay, so I'm going to carry on with the next supervised learning task. Okay, so this joint training with forward and backward language models is just at the pre-training stage, which means at this stage, we are training the models using unstructured data with unlabeled data. It's unsupervised task, right? And then after the models are trained and all the parameters are fixed, now we're gonna use the models for supervised NLP tasks. Like we want to, for example, given the sentence, given the input sentence that has n words here, right? We're gonna, for example, feed the model feed the input sentence into the model, and we will have 3 types of representations. First one, for the word n, we will have a word embedding, right? So that is a raw word embedding, okay? And at the first layer, we will have some first layer LSTM activation, and then we will have some second layer LSTM activation. So these are the representations returned by the model, and then we can combine, somehow collapse them into one representation, and then feed the collapsed representation to the downstream tasks, which can be a binary classification, or it can be a multimodal softmax classification models, okay? Depending on what tasks we are interested in, okay? All right. So the example here's an interesting example showing how the bidirectional language models using LSTM can actually differentiates the word senses based on the context. So, for example, when the input is like this one, Chico Reese played a spectacular play, made a spectacular play on a Lucix grounder, okay? So this word play have a different meaning as this word play, right? The second play means a Broadway play, right? It's a drama play, right? So a good model should be able to assign different meanings to these 2 plays, okay? So in the example that's this study has shown, that when we try to find the nearest neighbors of the play, the blue play is associated with, oops, the blue play here is associated with this play, right? As well as his all around excellent play, okay? And then the orange play here, the drama play, is associated with this play, which is a more, of course, looks more like a play in a sense, in the context of dramas, right? So this can be achieved by the LSTM, by the ELMo model, but for the same task, if we only use the GLAV vectors, which is just raw vectors, to find the nearest neighbors of this word play, then we can see that a lot of those words are mixed together, because it doesn't differentiate with the playing, the football, doesn't distinguish the musical play or the sports play or whatever other plays are there, right? So the model is successful in using the context information in a sentence to determine the meanings of a word, right? So that's why the model is, important. I mean, is really a impactful model in the year 2018. So the weakness of ELMo compared to the same the model that came out in the same year, like BERT and GPT, it's also very obvious that, first of all, the LSTM is way less powerful as an encoder than transformers. It uses much less parameters, okay? and also the two-way concatenation of the bidirectional language model might not as be as a all-directional fusion. Okay, so yeah, so that's why people develop very much more complex models like transformers. So we're gonna spend some time on transformers next when we in our Thursday's class. So we're gonna go through the details, some of the details of those. Would step inside the transformers model, and let's basically reveal the secrets of the performance behind. Okay, behind the performance, we're gonna see how those different building blocks can actually capture the semantic meanings really successfully. All right, so I think that's so much for today. We have made this transition from raw word embedding models to these deep contextualized in representations, which will be the basis for more advanced transformer-based models. Okay, so I think that's it. Glad to take questions if you have any questions.
This is not a question about the lecture, but I was just had a question about like the final and stuff like that. Since it's coming up in the next month, like are you gonna be giving like a study guide for that, or
Yeah, I'm gonna prepare a lecture. We're gonna talk about what's gonna what will be tested and how the questions will be like, questions like that, and how you can prepare the final exams.
All right, sounds good.
Yeah. Okay.